Okay, students. So today we will go back just a little bit, and because when I talk about some of the short circuits and open circuits and quarter wavelength line and half wavelength line, I will need to refer back to a few equations that we talked about in prior slides such as the wave impedance and input impedance slides. And so I want to go back to those slides and start from there for today's lecture, and then end up with uh, at the point where we start Smith lines or Smith charts. So wave impedance. So as I talked about in the last lecture, wave impedance is going to be the V sub D, which V is a function of D, where D is any position along the line, starting from 0, where the load is, and going back towards the source. And so D will increase in positive values as you go from the load to the source. And that's different from Z, where it was negative, 0 at the load again, but it got to be more and more negative values as you went closer to the source. We've switched over to using D, and D increases in value as you go away from the load towards the source. And so this wave impedance is going to be the ratio of the voltage over the current, or ratio of the voltage to the current, at any position D along the line. So we have the equations for V and I along the line. So we put those in there. The coefficient for I was V naught plus over Z, so the Z can come up here. And for the reflected component, there was the reflection coefficient, but you also had the minus sign there for the current, but for the voltage you had the plus. Okay, so the V pluses cancel out here and there, and you can bring out the Z naught in front, and you get this equation right here. Okay, and this quantity here is very important. This is something we will define as the phase shifted voltage reflection coefficient. Okay, it is the product of the regular reflection coefficient, but multiplied by a phase factor. And it's only a phase factor. It doesn't add anything to the magnitude of the reflection coefficient, just the phase of the reflection coefficient. And it's e to the minus j 2 beta d. All right? So when we express the reflection coefficient in terms of its magnitude and phase, we can combine these two phases together to get this. And so that's what goes in right here now, where this is the impedance, the wave impedance at any point in the line D. All right? And the magical thing about this, the reason why it's very good and very useful, is the fact that you can lump the impedance of the line and the load all together at these points D. And so replace V sub load and all of the effects of the line in with one parameter, one item that has this, one element that has this impedance Z sub D, Z as a function of D. All right, so it's very, very useful. Okay, but now if you let D go all the way back to the source, so D is equal to L, that's an especially important number, and that's called the input impedance of this whole transmission line. That includes the transmission line itself, but also the load. And so we take that wave impedance, that formula that we had on the prior page, and let D to be equal to L, the total length of the line, and then we label that as this Z sub N, the input impedance, all right? And so my D is now replaced with L, the total length of the line, in this phase shifted reflection coefficient, reflection coefficient here. And so this is what we have for the gamma, capital gamma sub L. All right. And so we can express that in a number of ways. We can use sines and cosines, and we can divide top and bottom by cosine to express it in terms of tangents, and that's all fine. Okay, and so that is the input impedance of the line, which includes the line and the load. All right. Fine. And so now if you want to calculate just the voltage dropped across the load, the line and the load, if both the line and the load, as well as the source, has impedances, then you have to do the voltage divider equation that you all know and love, and such that V sub I, the voltage at the input of the line, so right here, and not right there, this is V sub G, but now you're going to have a voltage drop across this element, and now we're interested in just the V sub I, then you know how to do that from your simple circuits class. You take this equation right there, okay? And but now so that's one equation that we have for V sub I phasor. But we have another one, the one that we've been working with up till now in this chapter, the phasor at z is equal to minus L, so we're back into the z notation, is this right here, all right? It doesn't matter, we could have used D notation as well, but then we just would have had the L here. So we have two equations, and we can solve for the unknown that we want. In this case, we want V naught plus, and this is what we have. So if we have all these quantities, V sub G, that's typically given, all the quantities we need to calculate the input impedance, if we have all those, as well as the excitation of the generator, the voltage of the generator, then we can calculate V naught plus. Okay, so the next example is to do just that. Actually, they want us to solve for the full voltage as a function of position and time, as well as the full current. All right? So they give us all of these quantities. They give us the fact that the frequency F is 1.05 gigahertz. They give us the impedance of the generator, 10 ohms. They give us that it is a 50 ohm line with a load that has a impedance of this, so it's both reactive and it has both a real part and an imaginary part. Gives us the length of the line and the fact that it's lossless. Gives us the speed of the wave down the line, and where c is the speed of light. So with all of that, we can just start deducing everything we need to calculate these two items, V and I. So one of the things we'll certainly need is the wavelength. And so the relationship between wavelength, speed of the wave, and frequency is this. We've covered that. And so this, when you put in the knowns, we get that the wavelength is 20 centimeters. And then we need to know this quantity beta times L for the phase shifted reflection coefficient. And so beta is 2 pi over lambda. We're given L, so we can find what this is right here, the beta L. So we first find just the regular reflection coefficient, and we have the Z sub L and Z naught. We plug that in and we get this. And so that puts us in a good position then, obviously, to find the phase shifted reflection coefficient. So we take what we calculated for the regular reflection coefficient, multiply to that that phase term that has as its exponent the beta L that we solved for previously. And then we're given this, and we can solve for the input impedance of the line given by this. Okay, and so that's one of the big things we need to use this equation right here. All right. Okay, but now we have to switch gears a little bit and work on the generator voltage. It's given to us in terms of sines, so we have to switch that over to cosine. So we know that to the argument we add 90 degrees. All right, And so they do a little bit of trickery here. But eventually they go back um, to, so we actually, I'm sorry, to go from a sine to a cosine, you subtract 90 degrees. So the omega t will carry through, and we have 90 minus 30 minus 90 is minus 60. So we get this right here, and then we have to go, if we want to go to the phasor, and we do, to get this right here, we have everything in cosine, and so then we have the phasor v sub g is 10 times e to the j 60 degrees. So that's right here, e to the j minus 60 degrees. So that's what we have. And so we have everything we need. We have the v sub g, the zn now, the beta l's, and we calculate v naught plus is this. So we can then write a v as a function of d anywhere along the line as this right here. All right. And so if we want to go back to the regular time domain, we can do that, of course, using this relation, and then this is what we have. So, and then when you have v, you can simply solve for I as well, very easily. All right. And so we're going to go over 4 special lines: short-circuited, open-circuited, half wavelength, and quarter wavelength lines. All are important for different reasons. Now, two of them are important for the same reason. They lead to a particularly useful procedure to measure the characteristic impedance of the line. All right, and those two are short-circuited line and open-circuited line. So for the short-circuited line, we had covered before and talked about that the reflection coefficient is -1. All right, so the backward propagating wave is equal in magnitude to the incoming propagating wave, but with a 180-degree phase difference. All right. So when you put that -1 into the equations for v and I, you get this relation. All right. And so then the wave impedance of this short-circuited line at any position d along the line is given by j z naught tangent beta d. All right. And so that's very interesting. So it's only an imaginary number if it's a lossless line, z naught. All right. And so we'll recall that the input impedance for a load of the impedance of a load of inductance L is given by j omega L. And so this kind of looks like this as long as tangent remains positive, because omega is positive, L is positive. And so this whole right-hand side is a positive imaginary number, has to be. And so if we're going to say this is essentially equal to an effective inductance, this short-circuited line, the tangent beta L has to remain positive. All right, because Z naught certainly is positive. All right. If it's not, then rather than an equivalent inductor, that the short-circuited line acting more like an equivalent inductor, it will act more like an equivalent capacitance because the J is on the denominator. All right, so if beta L is negative, then you know that when you take the J up to the numerator, you get a negative out here in front, and so the short-circuited line is acting more as if you had a line that ends in a load that is a capacitor. All right. So we have an example. Choose the length of a short-circuited 50 ohm lossless transmission line such that its input impedance at frequency is equal to 2.25 gigahertz is identical to that of a capacitor with a capacitance of 4 picofarads. And they give us the wave velocity. So they give us that Z naught is 50 ohms. It's short-circuited. They give us the frequency, the capacitance, and the wave velocity. All right, so those are all the knowns. And so we calculate first the beta. We need that to put it into our tangent beta L. Uh, and, and so tangent beta L, we're given the beta L is equal to, okay, so choose the length. All right, so we eventually want to solve for L, okay? And we're given C equivalent for picofarads, omega, 2 pi f, and f is this, and Z naught, 50 ohms. Okay, so we put in all those numbers here. We get this right there. We get the negative. And then we take the arc tangent of that, get it to the right quadrant so that it is negative, the inverse tangent, arc tangent. And we find that then beta L1, so one possible solution, is 2.8 radians, and we divide through by beta, which we solve for up here, and we get our answer. All right. That's not the only solution. We know that we can go to different quadrants and get another solution. All right. Okay, so that's the short-circuited line. Now we can go to the open-circuited line, where the transmission line just terminates without any connection at all. All right. And when we go back to our reflection coefficient equation and how that is dependent on the impedance of the load, if we have a load of infinite impedance, meaning an open circuit line, we find that the reflection coefficient is equal to positive 1. All right? Gamma, so this is supposed to be a gamma, is equal to positive 1. So we have positive 1 in here, minus 1 in there, and we get cosine and sine here, which is opposite of what we had for the short-circuited line. All right, so we get cosine here and sine there. When we take the ratio of V and I, we get a cotan instead of a tangent there. Okay. And so then we consider both of these and see what we can do with both of these. Okay, because these are very easy circuits to make with our transmission line. You simply put your load off to the side for a moment, and you first short the leads together, so you connect them up together, and then you measure with your network analyzer a input impedance, and then you let them terminate just in air, so it's an open circuit, and you measure the input impedance of that, and this is what you get. You will get two numbers, and the formulas, if you multiply these two things together, you see the cotan will cancel out with the tan. J times J is minus 1, but you have a negative there. And you have, so therefore you only have a Z naught squared on the right-hand side of the product of these two items, the Z short circuit and the Z open circuit. So you take the square root, and then that will allow for you to calculate this important number for the transmission line, namely the characteristic impedance of the line. All right, and that's great. And say, for example, you don't know the length of the line. Well, another thing you can do with these two relations is divide V short circuit by V open circuit and take the square root with a negative in there, and that gives you tan beta L. All right, so you can take the arctan, divide through by the beta, which is 2 pi over lambda, with lambda being the speed of the wave over the frequency, and you can get the length of the line. Okay, two important things about okay, so now we have two additional interesting scenarios or situations. One in which the line is equal to a half lambda, or lambda, or 3/2 lambda, or 2 lambda, or so forth. So integer multiples of lambda over 2. Okay, And then you put that into the equation for input impedance. Input impedance right here. And so if tangent beta L, if L is always lambda over 2 or lambda, then the tangent is always 0, and you get that the input impedance is always equal to only the load impedance, C sub L. Okay? So why is this important? Well, this means that you can choose the length of your transmission line, and remember, these are lossless transmission lines we're talking about. You can choose the length of your transmission line such that the effect of the line itself disappears. And you only have the impedance of the load itself. That's important in a lot of situations. And so that's a very useful technique. Another useful technique is to try to match the impedances of the load with the line. And you know now that if you do so, if you match the load and the line impedances, that you will have no reflection of the wave. And therefore, all of your power will be delivered and used by the load. So that is where the quarter wavelength transformer comes in. Because what you can do is that you can create another line that has a different characteristic impedance, Z02, and have it of a certain length such that the input impedance will be equal to the impedance of the first line. I do not know why this is doing this. Blinking like this. I think it's my pen. So that's very important. And so this input impedance of this portion, the second line and the load, is given by this, where Z0 will be Z02 and over ZL. All right. And so that will be my input impedance right here at this junction A prime. All right. So this example says, okay, we want to have the load, which is 100 ohms, which is not at all matched to the 50 ohms. We want to put in a quarter wavelength transformer so that Z sub n, the input impedance, is 50 ohms. And again, the Zn represents the impedance that the wave sees as it gets to this point right here, A prime. So if the input impedance is 50 ohms, this wave sees just the same material, the same type of wire as it's been going down. So there will be no reflection at all of the wave. All right. And that's important because without this additional part of this second transmission line, you would have a reflected component coming back to the generator, and therefore all of your energy will not be used by the system, the load. All right, and that's bad. And so if we do want the input to be 50, and we know that the load impedance is 100, that goes in here, we're able to calculate what my characteristic impedance of this quarter wavelength transformer has to be. It has to be 70.7 ohms. And then this will eliminate the reflection on the feed line. All right. It does not, by the way, eliminate them on the lambda over 4 line. You will have waves going back and forth and back and forth. But eventually, they all will make it to the load and be used by the load. Okay, so this is just a table that sort of collects all the useful information in the last couple sections of this chapter. All right, nothing else. Okay, so now we've covered those 4 special situations, but what we still have yet to do is to talk about instantaneous power flow. Instantaneous power flow, that's power as a function of time, and the power as a function of time is given by the product of voltage times the current, both being functions of time. And so we write the equation for Vt, so we go back to the time domain for V, back to the time domain for I. We take the product of the two, we do a little bit of math, and we get this down here, all right? And we see we have something with a positive beta d, which is forward propagating or propagating towards the load, and a negative beta d, which is propagating back towards the source. All right. Remember, we're using d's instead of z's. So we can then label those two terms separately. This is the incident power with the plus beta d, and this is the reflected power with minus beta d. Okay, so we can use some trig to change this trigonometry identities to change this cosine squared over to a cosine and a dc term, a term that's steady state or constant, and we get this. Incident power is equal to a coefficient out in front, but that's taken in, multiplied by 1, and then multiplied by this time-dependent term. All right. So we have a constant power being delivered to the system, and then we have an oscillatory power term, but with a frequency not just of omega, but of 2 omega. Okay, so interesting. The reflected power is also has a DC component, but now it's multiplied by the gamma squared, the reflection coefficient squared. And then it also has this time harmonic, this oscillatory term, but also with the frequency 2f, 2 omega. All right. So the power oscillates at twice the rate of the voltage or the current. All right. Typically, we're interested in the average power, and so therefore we're going to take the integral over this and then divide through by 1 period. That's not a hard integral at all to do. It is a constant term plus this cosine term. And the cosine term will not contribute anything. It's only the DC term. And so we get this for the incident power. And we get that incident power term, but multiplied by the reflection coefficient squared, magnitude squared. All right. The minus sign means it's going in the opposite direction. So the reflected power is equal to the average incident power, but diminished by a multiplicative factor of gamma squared. Yes. Okay. Okay. So I talked about the microwave, an interesting property that without any apparatus in a microwave, you can get standing waves such that your food doesn't heat up evenly across the entirety of the slice of pizza, or in this case, the chicken. And so they add in a couple of things to mitigate that. They add in certainly the rotating table, but also then this metal stirring fan that just basically just scatters microwave radiation. So you have, with a typical microwave, if you've never taken one apart, you have the magnetron. That magnetron launches the microwaves into the chamber, and then it is essentially a cavity, a metal resonant cavity, and it cooks the chicken. Kind of neat. And so it's interesting. I had heard some tales of how the effect was discovered. I don't know if it's true or not, and it's quite grisly. It's something where some military person stepped in front of a radar station that was just right at this frequency, and he came out cooked, essentially. And then somebody realized, hey, if it cooked him, it'd be good for cooking food. I can't believe that's true. I'm going to have to go and look that up again. But somewhere, somehow, somebody realized that this would be great for as a kitchen appliance, but only at a particular frequency uh, or range of frequencies. Because if the frequency is too high, it will only cook all the microwaves will be absorbed in the surface of the food and char that, but it won't cook the inside. Likewise, if the frequency is too low, it just simply won't be absorbed at all uh, by, by the chicken or the pizza. But right at the right frequency, the microwaves make it through a decent thickness of the food and are all consumed through heating of the food and therefore cooking. And so the frequency at which this occurs is when the molecules of water within the food are excited. And when they're excited, they are moving around faster. And that is heat. When molecules are excited, and thermal motion of molecules is what is heat in the material. And so water absorbs light or radiation at 2.5 gigahertz. So if you have a food that has water in it, the microwave oven will cook it. If you have food that doesn't have water in it, like dried beans or something like that, you'll find that it does not heat up very much. All right, so ceramic mugs, anything without any water, it will not heat up. So, um, so that's the microwave. So it's very interesting, instructive to look at microwaves, take them apart. Obviously, be very careful because there is extraordinarily high voltage. If you do take one apart, be extraordinarily careful not to touch, not to plug this thing in and touch the output of the high voltage transformer, because holy smokes, that will be instant death. But it's interesting to see how a microwave oven functions. Okay, so we are at the beginning of the Smith chart. And so that will be the start of the next lecture. Right? So you now, with this video, have everything you need to do the homework. All right, take care, students, and good luck. And email me any questions you may have, and I will respond as soon as possible.